get all these nuts. Got it. I need to get.
Thank you.
Right.
Very good then. So I think are we ready? So
Yeah. Only my mouse isn't. Oh yeah, it is working now. Okay, good. Great.
You may need to use a cursor because there's lots of people following on Zoom as well.
Yes. No.
Anyway, it's a pleasure to introduce Sabine van Dishoek to give the origin spoken this week. I mean, Sabine is a very difficult person to introduce because she's done so many things. Reading, she's the most scientific molecular astrophysicist in the world, which is amazing. I know she's written more papers than I've ever read. I remember that because I introduced her before. She's probably written more in the meantime. Well, just some recent highlights. The Hadley Prize was one where it was particularly great to see Sabine be awarded that for her groundbreaking work in astrochemistry. And she leads, she shepherded many telescopes and space missions to operation, ALMA and the James Webb in particular. And I think today she's going to be telling us about latest work from James Webb. So,
yeah. Okay, good. Good afternoon, everybody, and good morning, those of you in Virginia. It's a pleasure to be with you. Both in person.
Do you have a camera?
Oh, that is going to be a little bit difficult because it's not really working.
Oh, that doesn't matter.
Yeah, but that's sorry. Let me just try and get that. No, I don't have a spot anymore because of that. Yeah. All right. Apologies for those of you in Virginia who can't see me in person here, but I'm glad to see many people here in Chalmers, and it's a pleasure to be back. It's always fun to be here. Of course, my long-standing collaboration is John Black, and a lot of that is on molecules. And in fact, this morning we were talking a lot about some of the molecules that you see here, like water and CO2 and so on. All these molecules that we can now see with JWST. So this talk is actually going to be in two parts. I'm first give you some general introduction and talk more about the protostars, and then we'll have some questions, and then I'll go more into the disks, and then we have some more questions. But just to let you know that our overall goal here of our program is to follow basically the trail of gas and ice. Hello, hi. I'm seeing some good friends coming here into the audience. Great to see you. That's great to see you. You see that follow basically the trail of gas and ice from clouds to planets, from the very early stages that you see represented there. With simple molecules to the more complex molecules in star-forming regions, to disks, and then finally to planetary systems. And a few years ago, I was visiting actually Virginia, and I gave a colloquium there, and I talked mostly about the more complex molecules. Today, we're going to talk not just about complex molecules, we're actually going to talk about also the simple molecules, and we're going to talk about the ices, and especially the ices that start to form already in the early stages of star formation. Then get more complex in the more embedded phases when carbon monoxide is turned into methanol on the ices, and then get into the planetary system. But I saw already some of the projects that you were talking about is the first steps of planet formation. Where do the first steps of planet formation occur? Well, we actually think that they are occurring already in this much earlier stage, in the embedded stage, in the young disks, basically, where the grains already start to grow. So it's important that we study all of these phases, and especially here, this embedded phase of star formation, also to know what is happening in these later stages further on. So what are we using the molecules for? Well, first to get an inventory of the chemistry at each of these stages. What are the main reservoirs of carbon, oxygen, and nitrogen? Can we use them as a probe of the physics? We'll see actually examples of that. We'll talk a little bit about inheritance versus reset, and then ultimately what sets the exoplanet atmosphere composition. And a few years ago, I talked primarily about ALMA. Today, I'm going to talk almost exclusively about JWST and the infrared part of the story. But before I do that, I first want to thank everybody who has contributed to this work, and especially fantastic students and postdocs and colleagues, some of whom are here in the room, for making all of this possible. Okay, so how do we actually observe molecules? You're all used to ALMA and the infrared, the millimeter part, that we can use basically to study the rotation of molecules. But molecules can also vibrate, and they do so in the infrared. And you have a molecule like water, the stretching mode, which is at about 3 microns, and then you have the bending mode, which is at 6 microns. And that is the realm of JWST. Now, you actually get complementary information from these two wavelength regimes. ALMA is fantastic to get lots of complex molecules down to very low abundances, abundance of about 10 to the minus 12 with respect to hydrogen. We have also very high resolving power of at least 10 to the 7, and that means that we fully resolve line profiles. We can study their kinematics, everything. So that is fantastic for all the molecules which actually do have a dipole moment. But there are quite a number of molecules, and some of the most important carbon-bearing molecules like CH4, acetylene, C2H2, CO2, H2 itself, that basically do not have a dipole moment and that you cannot study with ALMA. But yet they are among the most abundant carbon-bearing species and also oxygen-bearing species that we have. For that, you need the infrared, and that's what we can do with JWST. But there's another very important difference with ALMA. ALMA only observes the gas. It's really that if we also want to study ice, we have to go to the infrared, because a molecule, once it's locked up in an ice matrix, it can still vibrate, but it can no longer end over end rotate there. In terms of abundances, we are sensitive to about abundances with respect to hydrogen of about 10 minus 8. Partly that's due to the fact that we have still limited resolving power, unless we go to the very high resolution spectrometers that are on the telescopes on the ground. But with JWST, we have about 3,000, but we will see we get a lot of science actually done with that. So I don't know how many of you are actually familiar with Webb. It certainly has had a lot of attention in the media. Webb actually has 4 instruments on board. You have cameras that can take beautiful pictures. So NIRCam, most of the beautiful pictures that you're seeing taken with NIRCam, but it also has spectrometers, and it has very clever spectrometers, not just taking a single spectrum at a single position, but there are these integral field units that you actually get a spectral map in one shot. And so the instruments that we are using is actually the mid-infrared instrument, the MIRI instrument, that's from 5 to 28 microns. And that's also the instrument that I've been very heavily involved in for more than 25 years. So it's good to see it now finally launched and working. This is a collaboration between Europe and the US. And on the European side, we had 10 countries, including the Netherlands, but also including Sweden. And in fact, Kay Justenon here from Chalmers has been leading that effort, and especially the hardware effort, for many, many years. So a tribute also to Kay that I'm doing here. And then there's also the other spectrometer instrument, the NIRSpec instrument, that covers the 1 to 5 micron range. And together, both because the telescope is of course a lot larger than previous instruments, detectors are better, the instruments are better, and so we have a sensitivity of a factor of 100 to 1,000 better than instruments, early instruments. So we have a real discovery space here with Webb. Since there are a lot of students here that may not be so familiar with infrared spectroscopy, I thought I'd give a little bit of a primer in infrared spectroscopy. So take a molecule like carbon monoxide, which can vibrate, but at the same time it can also rotate. And so you get, for the V equals 1 to 0, bands, you get this characteristic pattern. Is the delta J is -1 and delta J is +1. P and R branches shown there. So this is carbon monoxide at 500 Kelvin. Now, if you go to a molecule like CO2, it actually has a slightly different pattern. It also has a so-called Q branch, and you see a pattern like this. And then water is a very important molecule, but also a beast to work with. It has a very complicated spectrum, and this is the bending mode actually of water, again at 500 Kelvin. So you see that every molecule has its own pattern, and that's how you can recognize it. And it's again thanks to the tribute to many laboratory spectroscopists who were able to get us all of these data, and we're still finding new molecules that we need data. There's another thing you can very rapidly see from all of these spectra, and that's the temperature. Just take CO at 200 Kelvin, 500 Kelvin, and 1000 Kelvin, you see the different patterns. And so that's another way in which you can use these molecules to learn something about physics, just from the temperature. And then there's a third thing that you need to know, and that is gas versus ice. A gas phase molecule can vibrate and rotate. So you get this nice vibration rotation spectrum. When the molecule is locked up in the ice, it can still vibrate, but it can no longer rotate. And so this whole structure that is here in the rotational bands collapses to a single broad feature that is due to the ice. You can see these lines from the gas phase, of course, both in emission and in absorption. The ice we will generally see in absorption. That's why I'm plotting it here as an absorption rather than what we were doing here in emission. But there's another thing about these ices, and that is if a molecule is locked up in this only having CO as its neighbors, it has a slightly different profile from one that has water as a neighbor, because the force constants will be slightly different. It will feel slightly different molecular forces. And that we can actually see in the spectra. So this is for the 15 micron CO2 band. Pure CO2 ice has a very different pattern than, for example, CO2 in a water ice matrix. So that's another diagnostic that we have, that the ice shape really depends on environment and on temperature. So these are some of the diagnostics that we will use. Okay, so I'm going to talk to you about some of our results. These are all from cycle 1. And because we spent 25 years and invested national money into building MIRI, we actually also got, as a consortium, guaranteed time. And we put that guaranteed time into several substantial programs. And one of them is the Protostars program that I'm leading. And we also have our US colleagues that helped build MIRI. In fact, Mike Gressler was the instrument scientist. That we're also putting some of their time on Protostars. So we have a combined program that we call JWST Plus on Protostars. Then we also have the protoplanetary disks, the MINDS team, led by Thomas Henning and Kamp, but also with a significant involvement from Leiden. And then there are some open time programs, the ERS program Ice Age, led by Melissa McClure, investigating protostar accretion from Tom McGeeth, and the Corinos projects from Yuan Yang. So what I can do here in this very limited time is only give you a little bit of a flavor of what these programs do, but I hope that this gives you an impression of what JWST is capable of and how you can use it. So let's start actually with JWST. So if you want to meet more about it, go to MIRI STRW leidenunif.nl. We actually got most of our data only in fall 2023. So we were running a little bit behind most of the cycle 1 projects because we got our data very late. But this is actually thanks to my thanks to the JWST team, and especially here to Harold Linhuis, who was leading the laboratory in Leiden, but who tragically passed away on New Year's Eve last year. And so he was a key member also of our collaboration. So to remind you, embedded protostars are actually complex systems because on a scale of several hundred AU, many processes are actually taking place. We have the protostar itself that is still growing. The young star is still accreting matter. We have a disk that is forming. It's having an outflow with jets and wide angle winds. And there is still an envelope, a remnant envelope that is actually falling in into this disk. So all of these processes are occurring simultaneously, and previous missions such as Spitzer were able to only have a single pixel here on the sky and have all of this in one blur. And now with our integral field unit, we can actually dissect this. We can actually get a spectral image of all of these different components. And this IFU of JWST is really extremely well matched to these systems. Whether you look at a low mass system, you have about 30 AU resolution. A high mass system, you have about, say, 150 AU. And so there are many different science questions that you can address with a single data set. Here, I'm only going to focus on a few of them. So let me first show our poster child image. This is actually a NIRCam image of the HH211 jet, the class 0 protostar, still very young. You can't even see even with JWST, you can't see the protostar yet, still completely obscured behind dust, but you of course do see the beautiful jet here, and you see it in all of the different components, including the molecular and the atomic and the ionized parts. Its age is only about 1,000 years, so it's still a very young system. So this happens when you put it, submit it to nature, and then you get it on the cover of Nature. It turns it around and gives it different colors, but it is still the same object as we see over here. And so there's a lot to tell about this also in terms of the jet physics, which I won't go into detail, but just give you a little bit of a taste of it. What we generally see in both HH211, but also in other systems, this is a serpent source. We generally see iron 2 at 5 microns, this MIRI as a jet. And then we see the molecular hydrogen is much broader. It's really sort of inside the outflow cavity, and it is tracing a disk wind. And you can really connect this also very nicely with ALMA. So it's really also the era of the synergy between ALMA and JWST that you can see all of this now in this way. And this is something, this whole pattern of iron 2 in the jet and H2 in the wind, we see it basically in all the class 0, 1, and also in the high mass sources. Just as a teaser, this is not a single source, but this is a binary. This is a class 1 binary, TMC1, about 100 AU apart. And what we now see is that they're actually different. I mean, one of them, the Western source, has an iron plus jet. The other one is the one that has the wide angle wind. And we think actually that there's an accretion stream entering into this source over here that is triggering sort of this wide angle wind. And so also we see some diversity in that sense between different sources. The HR71, one of the favorite sources, also from John Tobin and others. It's a beautiful outflow that you see here in the Spitzer and in the JHK image. And now we focus actually in a 3x3 mosaic on the inner part. You see a beautiful sort of teardrop here of the inner part of the outflow structure. Again, in molecular hydrogen, you also start to see sort of the shock structures here inside. Now you go to iron 2, and there's the jet, beautifully seen. And now we go to a noble gas, like neon plus, and we see it also in the jet, but we generally see it also a little bit more broadly distributed. So we can now really compare in many, many different lines, both the molecular hydrogen, the refractory elements. We have not just iron, we also have cobalt, nickel, chlorine, sulfur, other molecules and atoms. And then we also have the noble gases. So this is a pattern that you will see emerging now over the next months, I think, in several publications. Okay, so that was basically focusing on these very strong lines that we see in all of these protostellar spectra. But in general, these protostellar spectra look like a rising continuum with superposed on it these very deep absorptions due to silicates, due to ices, that we have maybe with some PAH is superposed. What you see here is actually our first and only source that we had for a long time in our program for more than a year, which was a high mass protostar, actually, at a large distance, actually in the outer galaxy at 11 kiloparsec, which turned out to be a nice binary. What I'm going to use it here is to look at this part of the CO2 ice Because if you look at that more carefully, then you start to see that it's not just ice, but you actually see the gas superposed on it. This is the power of MIRI. We now have the spectral resolution to see not just the ice, we see the ice and all the gory details of the different ice components, but we also see the gas phase lines superposed on it, this Q branch that I was mentioning, and then here the R branch and the P branch. Now, just looking at this pattern of lines, you can simply read off the temperature. You don't need to do any complicated analysis. You can almost read it off there. It's actually quite cool, surprisingly cool, only 150 Kelvin. And we don't see the water lines in this part of the spectrum, also surprising. So what is happening here? A little bit of chemistry. Maybe you're looking at what CO actually reacts with. So some simple chemistry, OH reacts with CO, especially below 250 Kelvin to go to CO2. This reaction, this H2, has an energy barrier, and it will start to proceed only above about 250 Kelvin. That's when you start driving it to water. So maybe the fact that we are at 150 Kelvin points us to an environment that is relatively cold, rather than being sort of the usual, several hundred Kelvin shocks or even more that we have. So one interpretation, what we're looking at is, because this is a high mass source, is that we're actually looking at the cool emitting region in the upper layers of a disk at fairly large distances. We know that these disks have a warm midplane due to the high accretion rate, where we see water in absorption, and we see actually water in absorption also in our system. And maybe the CO2 at 150 Kelvin is coming here from the outer part of the disk. We're looking here at one quadrant of a protoplanetary disk as a function of radius and height, that we're maybe coming from this part of the disk. So just to give you an impression of the kind of science that you can do with these data. We see actually at some positions extremely rich molecular spectra. This is at another low mass class 0 source, a well-known outflow source of 1448. In this case, it's really full of water lines. This is really a warm source to some degree. We also see CH4 for the first time, is the Q branch, and also surprisingly, SiO is actually seen in emission. SO2 is also seen for the first time in some of these sources. And of course, here we see the tail of the CO bands that you can again use to read off the temperature. Okay, and this is to show that we see it not just in emission, but we also see it in absorption. And this is our poster child, B1C, again, a class 0 source, where all of these lines are actually in the hot core towards the continuum of the protostar. And this is just a simple fit that Logan Francis made, all credit to him, for both water, CH4. Now we get actually into the region. You see, we haven't identified all the features yet, but now we get into the part where we actually have the C2H2 is coming. We're getting to 13 microns now, 12 microns, yes, there it's starting to come. Here we get actually into that is where we get into the acetylene. The acetylene in absorption, there's the Q branch. Now we get the HCN in absorption, and now that's the CO2 actually very nicely. There's the CO2 in absorption. And so again, this is just to give you a taster of the kind of data. Here's again the water lines, beautiful fits. Again, a simple LTE fit already works extremely to see all of these water lines there. Okay, good. So just to summarize, we have in terms of the gas phase molecules, we detect already new species, and we see diagnostics of hot porous accretion shot jets and young disks that we haven't seen before. Before we break, I want to do one more thing and say a few words about ICES, because that's also what we see in our spectra in the protostars. And this story actually starts in the dark clouds. This is the dark cloud in Chameleon, where you have two background sources. So the experiment that we're doing is basically we have a star that is behind a cloud, and we go through the cloud, and then we look actually at the absorption, this JWST superposed on the spectrum of the star. and we have background stars with extinctions of 60 to 95 magnitudes. So here the dashed line is actually, the dotted line is the continuum of the star. And now we see all of these very deep absorptions that are eaten out of that continuum by water ice, by CO2 ice, by CO ice, and by also minor ices. So this is before star formation. This is before the cloud collapses to form a new star. And this is sort of our ground zero as to what the ice inventory is before star formation. Okay, so keep that in mind. Keep also in mind the incredible sensitivity that we have with JWST. This is near spec. We are here at 10 microjenskis. You know, we were used to looking at sources that were jenskis, and here we are now at 10 microjenskis. So the quality of the data is just absolutely phenomenal. We also now go to protostars. So normal stars have a falling spectrum. This one has a rising spectrum. This is from the IPA program. You see again the CO row formational lines. You see all these deep ice absorption features, including here the 13 CO2 ice. And just this is a very nice study that was recently done by Shanti Brunken using the Leiden ice database to look at the structure of the 13 CO2 ice. And what you see already is that there are some sources that have very similar features. There are other sources that have clearly an extra feature. And that shows that these ices have been heated and segregated due to these are also the most luminous sources in the IPA sample that you see clearly reflected in the ices. So whenever you have an accretion event, for example, that would heat the envelope and that would start to induce sort of a segregation of ices that you see actually here reflected in these spectra. And you see that also very nicely in the 12 CO2 bending mode as we saw in some of those laboratory spectra. But the most exciting recent results we have actually had on the very weak features. It's actually one of my sayings, favorite sayings, is that most of the new science is in the weak features, not in the strong features. And if we look again here at the protostar spectrum, here this beautiful spectrum by Zhou Lun, that we actually focus now on this part of the spectrum, so right over here, because this is where complex molecules actually have their fingerprint region. So we subtract the baseline, that's a whole continuum, it's a whole story in itself, but once we've done that, we get a spectrum that looks something like this. And now we start to fit this with ices. We see clearly bumps and wiggles in here. Are they real? Are they not real? We think they are all real. This is CH4 ice, clearly present there. OCN minus ice, SO2 ice, HCOO minus ice. These were some of these were suggested already earlier in the literature, but we finally see them beautifully confirmed. Ethanol ice, formic acids. So we go to more and more complex molecules, use the Leiden ice database, and we also test for statistically how robust these are. And this is the final fits that we then get. So why is this important? This is actually the first detection, robust detection of complex molecules besides methanol actually in ices. There has been a big debate in the literature how these complex molecules are formed. Are they formed in the ices or are they formed in the gas phase? And part of the proof of the pudding is to actually see them in the ices itself. Now you can quibble about some of these features about their identification, but we now have multiple sources where we get a very similar pattern and also very similar fits to these spectra. Also note that these ices are actually very salty. These are salts together with ammonia, so they are not just full of alcohol, but they are also full of salty alcohols. And that's what led some of the press releases to talk about margaritas in space, even though we never mentioned that word, but the press actually like to talk about margaritas, but also vinegar that we had there. So these are just some of the examples of press releases that this paper that came out on March 13 was actually giving us. Okay, I think I'll stop here and invite first a set of questions on this part of the talk.
So, yeah,
and I know
planet, you have a second part of it.
Yeah.
How long is that? Second part?
It's about 15 minutes.
15 minutes. So yeah, we'll have about 5 minutes of questions now and discussion, and then maybe we'll do another part on the disks. So are there questions in Virginia? Ryan, please, perhaps you can help tell me if there are questions there. And we can start here with Gina.
So I was wondering about your last comment, actually. So seeing these molecules in the ice, does that mean that they were wiped out after they were put in the gases?
Yeah, that's a very good question. So the question is whether they were formed in the gas phase and then frozen out, or whether they were formed in the ices. We think actually that you cannot produce enough of them just in the gas phase, even though we see them in pre-stellar cores, also in the gas phase, at least some of them. But in much lower abundances than we find here. The abundances that we find in the ices are a factor of 1,000 or more than we would ever have in the gas phase. The same story for water, actually. You cannot make all of the water that we see in the ice in the gas phase and then freezing it out. There's simply too much of it in the ices. So we must actually form it in the ices. It doesn't mean that subsequent gas phase chemistry cannot happen also once they are released back in the gas in a hot core. But at least seeing them here in the ices is proof that we are forming them there.
I had a question. Can you comment about our ability to measure fractionation or deuteration of fractionation in general in the ices or in the gas? I suppose.
Well, yeah, I mean, we and other groups are working on papers to get 12C over 13C, so that is the easiest one. And there have been already results on that from the isotime on massive protostars. So that is a good one. I think nitrogen is almost impossible because it's we see the ocean minus and the ammonia, but we no chance of seeing the 50 nitrogen. That's simply too weak. But we do see the deuterium. There's a paper out just now on AstroPH since only a couple of weeks on using the IPA data. We have a robust detection of HDO ice for the first time. And this HDO over water ratios that are actually very consistent with what was derived from the gas phase. So with the scenario then being these were all massive intermediate and high mass protostars from the IPA program, that's what we are seeing in the gas is the sublimating ices actually. And there's definitely fractionation in these HDO. So I was actually, those were the slides that I took out in order to save time. But I'm happy to talk about them.
Raise your hand in Zoom. Brant next.
Yeah, so I really like, statistics on these ices, but if you look at the fit, there's still some things that are slightly missing. Is it kind of thought that these things that are kind of missing are molecules that just aren't in the LIDA database, or is it that in the grand scheme of things you don't just have simple pure ices that add up nice and simple, you have a truly complex mixed ice, and that this might.
Well, we have of course some ground truth. If we believe in the scenario that what we see in the hot cores is sublimating ices, then we know the ones that are most abundant, and that's actually a study that's comparing what we see in the gas and the ices that another PhD student, Yuan Chen, has just done on some of these same sources, and that paper has just been submitted. And there you see indeed a correspondence between what we see in the gas and in the ice. This particular feature, we think we have a new identification for, but I'll leave that to Will Rochet to tell us about it. It's an interesting identification, but we're not yet fully sure of it. But we see the feature. I mean, at this time we didn't know how common this feature was. Now we know that it is.
Yeah. A question from Jian Li.
So in some of the low mass sources, you showed collimated jet in iron and in molecular hydrogen.
Can you speak a little louder, Lee?
Yes. Yeah, I was asking about the molecular hydrogen, and you label that as a disk wind. So I'm wondering whether there's any direct evidence that the molecular hydrogen outflow is coming from a disk itself, rather than some.
Yeah. I understand what you mean. Whether the H2 is truly a disk wind or.
Can you repeat the question?
Yeah, so the question is whether the H2 is truly a disk wind, in which case one would like to see the rotation also. Perhaps, of course, we don't have the velocity resolution to see any rotation in the wind, but it's more from the pattern that we see that is I would say is consistent with the disk wind, which is why we interpret it in that way. But and it's clearly inside the outflow cavity. It's definitely not entrained material along the outflow cavity walls. Yeah.
Okay, last question before we go on. Gunnar, go ahead.
This is probably very naive, but you had one picture where you showed, I think, CO2 in the gas phase and CO2 in ice in the same picture. Now, are they taken in the same direction, and how do you then sort out the...
Yeah, no, very good. And in fact, we know that the ice must be in front of the gas phase because we see the ice extincting the P branch of the CO2. So what oh, we even have a blackboard here. I would always draw and say, yeah. So basically, the picture. Yeah. The picture that we have is here we have our protostar, and here we have our high temperature region, and here we have our low temperature region. So if I look along the line of sight here, then here is where the ice is, and here is where the gas is. So here is basically 20 Kelvin, and here would be 100 Kelvin or so. So you have basically along the line of sight. So this is where the CO2 emission would come from, or it would come from our interpretation here from a disk surface that is inside. But we clearly see it extincted by the ice, which is along the line of sight that we are looking at.
So you get the same observation and
Yeah.
you have to sort out.
Yeah.
Great. I think we should move on to your second part then.
Yeah, okay, good. Thanks for all that. So now we're moving from the embedded stage of star formation to the disk phase. And of course, there's absolutely fantastic work by ALMA being done here. And here's from the cartoon from the MAPS program, led by Karen Neuberg, that I like a lot. And then here is basically the complementarity as to what JWST does. JWST then looks at the gas here in the inner part, and then also at the ices in the edge-on case in the outer disk. So a little bit of introduction for those of you that are not so familiar with sort of the main questions in this area. And one of the main questions is basically what the abundances are in the gas and the ice of the various elements. And if you look at sort of at the temperature gradient, we of course know that a star heats a disk and is warm close to the star, and it's cold further out. So you have the temperature gradient, and that means that you have the so-called snow lines, ice lines that occur here at 20 Kelvin, 50 Kelvin, and say 150 Kelvin. And because the ices are always oxygen rich, it means that your C overall will be low in the ices, but it will then be high in the gas phase. But then there's also this fact that if you have a little dust grain over there, then the larger dust grains are no longer coupled to the gas, and they move at a slightly different velocity, and so they will actually drift inward and cross these different snow lines, and then basically start to sublimate. So what we get is a structure of a disk that has these large dust grains actually piled up in the inner disk, and they will be very oxygen rich. And what is left in the outer disk, that is what they actually measure with ALMA, is a gas, still the smaller dust, also a little bit of larger dust, but mostly the smaller dust with the gas that is overall depleted in carbon and oxygen, but has overall a high C/O ratio. Whereas, and that's actually what we observe for many disks. But if this actually is able to drift inward and cross the snow lines, then they will start to sublimate, and then you get all of this ice that you have here into the inner disk, and that will give you actually a high abundance of oxygen in the inner disk. Now, all of this changes when you introduce a planet. Then you get one of these beautiful dust traps that we see in the ALMA images. and that locks up actually a lot of icy pebbles in there. And that means that, you know, we basically block the supply of oxygen and carbon to the inner disk, and you would expect in this part that JWST is measuring, you would expect actually very low abundances. So the composition of the inner disk and any planets that may be forming there depends very sensitively on the presence of dust traps, and also whether those dust traps are actually inside or outside snow lines. So this is actually the MINDS team that has looked with the GTO time at some 30 Titori disks and brown dwarf disks. This was our first publication, one of the earliest sources that was observed. What you see here, you see again the rising spectrum, you see the silicate features. That was known obviously from Spitzer, but now you see on top of this, this is not noise. All of these are real features. So you see here again the pattern of the carbon monoxide lines, the irregular pattern of the water lines that you see here, and here we see again our friend, the CO2 appearing there. And we see not just 12 CO2, but we see actually also the 13 CO2, and we see some of the hub bands of the CO2 actually occurring there. So this is a blow up. We now know that all of these features here are real, and they are not noise. We can fit them very nicely with just a simple, what we call SLAP model, where the only variation is the temperature and the density, column density, and the emitting area, and we can fit these spectra extremely well with these kinds of plots. The main conclusion from this is actually that CO2 over water is much higher than previously thought. And one of the questions was, well, how about other disks? So this is a paper that will soon be on AstroPH. It's about to be accepted on DR tau. Our DR tau is actually a rather compact millimeter disk seen with ALMA in Taurus, where we would expect this effect of these drifting icy pebbles and then enhancing it to be maximum. This spectrum is really chock full of water lines. This is work by Milou Tamming. And now you can actually fit these water lines not just with one temperature, but you can actually look at a temperature gradient, both with wavelengths, but you can also do that as a function of radius. So with wavelengths is also related to sort of emitting area and where to radius, and then you see that you nicely uncover sort of a temperature gradient in the inner disk, which is very abundant in water. So you can start to test also some of these thermochemical models that have been developed for that. But just to put things in perspective, so this was the first disk that we had with the very strong CO2. This was the disk with the very strong water, and I just want to put them on the same flux scale to show you that this first disk that we got was actually a difficult disk to study because it was one of the weaker disks compared with some of the other later disks that we actually got. But we definitely do see a variation among the Titori disks. I mean, some Titori disks are very rich in water, others are really CO2 rich. Hints were of that in the Spitzer data, but now we see it even more clearly. And so there's some nice modeling work that has been done by Marissa Flasbaum that shows you if you have the effect, if you have a drift-dominated disk, you would actually get very strong water lines, like we may be seeing in this particular source, and like in DR tau. Whereas in GW loop, they actually have perhaps, and this is something for ALMA to test, a very small cavity of only 1 AU or so, that would deplete the inner disk of the water, but still have the CO2 rich there. So this is sort of where we are now in terms of testing sort of inner disk structure with these various different lines that we see. And this is something that ALMA cannot do because ALMA cannot get into that inner few AU or only with great difficulty. So we really have a new tool in hand now to test sort of inner disk structure. And so there's also some nice modeling work that is ongoing here in terms of bringing in sort of another explanation would be sort of a time effect where you first bring in the water ice water-rich ice grains, and then in a later stage, the CO2-rich ice grains, so that it will be a slight difference in sort of age between these CO2-rich and water-rich groups of that. So now we're looking at larger samples of sources in order to test this. One very interesting source was definitely also PDS-70. I saw it already on one of your slides that, or maybe it was in Virginia, somebody looking at PDS-70. Well, we also looked at PDS-70 with water, and we actually do see the water lines there. And it's a bit of a surprise because this source has a huge dust trap. So this is the inner part where the terrestrial planets are formed. We know that there are 2 young planets there over there. But in spite of this very strong dust trap, there is still some oxygen leaking into the inner part, some water that is still there that we see very prominently here in these lines at about 600 Kelvin. Okay, so that's sort of on the Titori stars. Our biggest surprise actually came on the very low mass stars. And this is a very low mass stars, J1605 in Upper Scorpius. Which was known from Spitzer, from the work of Ilaria Pascucci, to have these 2 big bumps, but nobody could understand what this was. Was this a silicate feature in absorption? What was this? What were we looking at? And it was really thanks to Benoit Tabon who figured out that these big bumps were actually tons and truckloads of acetylene. Acetylene that is not just abundant, but is very abundant by 4 orders of magnitude compared with what you normally would derive. This disk is just incredibly rich in lines, also in hydrogen lines, hydrogen recombination lines, molecular hydrogen lines, all in a paper by Franceschi that is just been published. No silicates. We can probably look very deep into the disk in this particular case. We also see benzene in this disk for the first time. So just to show you the difference in terms of ratios compared with the Titori stars, it's almost 5 orders of magnitude difference in terms of the acetylene column density, and acetylene of CO2 is still some 2 orders of magnitude. So it's both an enhancement of carbon, but we think that we also need at the same time a decrease actually in the oxygen. Because we don't see any water, even though it's warm, it's 500 Kelvin. So we probably need to lock up some of the water as well. So that leads us to these kinds of cartoons where we have sort of an inner disk that is very carbon rich in this inner part, perhaps even due to destructions of carbon rich grains. That's still under debate. We may have a gap again. And then we are locking up the water ice somewhere outside in the disk that prevents it from coming inward. This is one possible scenario. It's an alternative scenario is hydrocarbons actually drifting in. But it is certainly an intriguing source because this is actually one of the scenarios that is also being proposed as to why our own early Earth is actually so carbon poor, and that if these carbon rich grains and gas were actually removed in these early stages, they may actually make very carbon poor planets, like what happened to the early Earth in our solar system. Okay, the next question is, how common are these hydrocarbon rich disks? Well, this is a nice plot by Sierra Grant. We actually think that the bulk of the very low mass stars, so very low mass stars, say below 0.2 solar masses, close to the brown dwarf limits, also the brown dwarf themselves, they are all very rich in hydrocarbons. The Titori stars are clearly much lower, some of them even very low. And so this is under construction for your eyes only, but will hopefully soon come out now. This is one of these, actually the most hydrocarbon rich, very low mass stars, worked by Aditya Anabavi, where we see here CH4, there's no continuum due to silicates. We see CH4, we see C2H4, then we see C2H6, for the first time and outside our solar system. Again, we see acetylene, although not as dramatic as in the other one. The 13C HCN, benzene, CO2, HC3N, 13CO2, C3H4, C4, and diacetylene. I mean, all of these molecules are just waving at us. And again, it's a very language spectrum. Okay, so this is just a summary, main drivers of inner disk chemistry. You can have this radial drift, you can have trapping of dust, you have the dust grain and settling that is moving inwards. All of this is playing a role, and it's playing a role differently in different systems, and especially these very low mass stars turn out to be different compared to some of the other systems. So I'll stop here, and I hope I've given you a taste of what JWST is able to do in clouds, in protostars, in disks, and setting the stage for making the connection with exoplanets and brown dwarfs. Thank you.
Okay, so we have the time for about 10 minutes of questions or discussion, further discussion. So in the Zoom, please raise your hand. And again, Virginia, maybe we can start in Virginia if there are questions there.
Jonathan, could I ask a question?
Yeah, for some reason the sound is low, so we just need your volume up.
Yeah, that's what I had it.
Hi, thank you for the presentation. I was just wondering if you've seen CH3 plus towards any of the disks in mind.
Hang on, Ryan, we're just trying to fix.
Yeah. Ah, yeah.
Can I try again?
How's this? Is this okay?
Yeah, it's okay. We can hear you. Yes. Okay, go ahead.
Hi, thanks for the talk. I was wondering if you've seen CH3 plus towards any of the disks in Mines or even the protostars in JWST, but still just that one disk in Orion that we've seen that detection.
Yeah, that's a good question.
Can you repeat the question?
Yeah, the question is whether we see it. So one of the beautiful results from the PDRs for All program, a fantastic JWST program on PDRs, but one of their, inside the Orion PDR, there's also a little disk there that's a heavily irradiated disk. And one of the beautiful discoveries there is the detection of CH3+. That has been seen. So following that discussion, we have indeed been looking at it. I'm pretty sure we see it in one disk. I don't think we see it very commonly. I also don't think we see it in any of the JWST sources. But I do think we see it in that one disk. Yeah.
Mm-hmm. I had a question about how well we can measure pebble accretion, pebble flux rates, or mass delivery rates from the data.
Ah, well, that's a good goal. Yes, that we would like. So I think the difficulty that we've had so far, we and all the teams, is we have gorgeous spectra where we see all of these hundreds of lines. We have beautiful fits to them. But then if you look at the sort of the uncertainties in the derived column densities and abundances, they are actually very large because there's some degeneracy, for especially between column density and emitting area. And for the optically thin lines, for the optically thick lines, of course, we have to deal with optical depth effects. And that means that our uncertainty, our error bars are at the moment pretty large on any abundances. So if you ask the question, is the water abundance in the inner disk, say, enhanced compared with what you would expect, 10⁻⁴, is it as large as 10⁻³ or 10⁻² even, what you expect in these models that are delivering lots of water-rich icy pebbles? We cannot answer that question yet. But it's actually interesting to see because maybe as a disk community, we are a little bit too conservative because our exoplanets colleagues, they are having also interesting JWST spectra. If you look at their derived abundances, they're tiny little error bars, and they don't see all of the individual lines. So there is a little bit of maybe we are as a community much more conservative than the exoplanet community in terms of deriving abundances. But it's obviously something that you want to try to address with these data set is you need to measure the abundances accurately in the
so you can measure relative abundances of certain species, but you can't measure absolute abundances.
Well, even the relative ones between optically thick species are difficult because each of them have still uncertainties. And for optically thin molecules, then we also have to think, are they emitted from the same part of the disk? We know from the chemical models that they, one molecule may be a little bit deeper in the disk than the other one. So any abundance ratios or column density ratios are not necessarily representing sort of.
So then we'll never get the good C2R ratio.
Oh, well, I'm not that pessimistic. I'm just saying at the moment we are careful in saying that don't take any numbers blindly and draw conclusions from them. But it's obviously a next goal. And with such beautiful data, I'm sure we'll crack it at some stage.
So you'll need a good physical model.
You need a good physical model, and you need to look at the right lines. Yeah.
Are there other questions in Virginia there?
Yes, Jonathan, from Ifan.
Hello.
Yeah, thanks for. Can you hear me?
Yeah.
Thank you very much for this great talk. So I want to touch on maybe continuing on the communication between the exoplanet community and the disk community, and your last point about the connection between like a disk and the exoplanet and brown dwarf. So you show this great diversity of chemistry among disks, and I think this is kind of like in stark contrast to the Oberg 2011 picture, which is fairly simple, and the exoplanet people tend to use that as a backbone to interpret their compositional measurement to probe like where the planet form. But given this diversity, I guess where do you see is the next step in helping us to make a concrete progress in connecting exoplanet and the disk measurements?
Yeah, that's a very good question. Yeah, so the question is how can we make progress in connecting then exoplanets atmospheres with their formation location, and it's certainly not as simple as in the simple Oberg et al. Plot. I also don't think they ever meant it to be that simple. In their defense, they never meant it to be that simple. But it's clear that we're now seeing these effects appearing. I think it's critical as to when and not just where the dust traps form, but also when they form. I mean, how early in the system is that happening? There was earlier the question on the on how the isotope ratios can help. They can certainly help a little bit, and that's why I'm here at this brown dwarf, making at least that connection, because brown dwarf spectra are gorgeous with MIRI. I mean, this is the ammonia band of the brown dwarfs, and actually, if you look very carefully at their models, you see that there's something missing here. This is actually 15 NH3. And then if you measure sort of the abundance here of this 15 ammonia in this brown dwarf, you get actually a very high value compared with comets, compared with solar system objects, also compared with the ISM. So that is another interesting clue as to how you could start and try to connect and come up with scenarios that could give you such a depletion. But I think for the moment, we just need to look at many more sources. We have so far done detailed analysis of only a handful of sources. Thanks to several programs, not just in cycle 1, but also cycle 2, will be close to 200 disks being observed with JWST. So both in JDisk cycle 1, but also Ilse's program from DECO in cycle 2 and HPRO in cycle 2. So I think by the end of cycle 2, when we have sort of a few hundred disks, we should be in, and if those disks are also observed with ALMA at very high spatial resolution, then I think we are in a much better situation to start addressing this question.
Are there other questions in Virginia? Or here we have Nilüfer.
Thank you for your talk. I have a question about the low mass stars, like the dwarf stars that are forming. You showed that they have different characteristics when it comes to their carbon and oxygen abundances. I was wondering if you can talk a little bit more about why that's the case. Is that something that when, like as somebody who works on planet formation, do I need to consider if I'm looking at the formation of planet around a low mass star, like would I need a different model now? Or-
Yeah. So that is that's indeed a good question. We don't know the answer to that either yet. So because on the one hand, things are happening quicker in these low mass stars, so you could say that maybe all the water has already drifted into the low mass stars there, and we are now seeing all of these hydrocarbons that formed on the grains in the outside part and that are now drifting inward. So we're catching all of these very low mass stars just at the time when the hydrocarbons are drifting in. I'm a little bit uncomfortable with that explanation because there's definitely an age range. And as we've seen already from some of these models, these are the models from, what is it? Where did I have that? No, from Kalian et al., but also the ones, here, from Andrew Selleck. So the hydrocarbon peak would be a little bit later still than here. It's still pretty narrow range in ages, and I think we have a much larger spread in ages of these systems. So while the sort of differential time of the drift can play a role, I'm not sure that's the full story. Wow.
Maybe the inside-out planet formation models we're working on, predict where the trap should be at different stages. So we need to look and see if systematically the subline will become more apparent when you go to low mass systems. We'll think about that. Okay, we should stop now, and we're going to thank Abine again.
All right.
12-minute break now. I'm going to close the room to make the recording, so rejoin in 12 minutes if you're staying for the workshop.